Welcome. In this lecture, we are going to talk about design case study. We are going to consider design case study and MATLAB simulation of digital voltage mode control. So, here we will first consider some design case study of digital voltage mode control buck converter. Then we will consider design case study of digital voltage mode control boost converter along with their simulation, MATLAB simulation for both as well as buck and boost converter. So, here this is the continuation of I think lecture number 43, where we have discussed the design methodology for digitally controlled voltage mode control buck as well as boost converter. So, we are taking those results. So, this is the typical diagram of analog voltage mode control, and if we are going for PID controller tuning, then we have discussed that we can go for stable pole zero cancellation, that is the method 1, where we can set this parameter K1, K2, these are the simplified version of the practical PID controller, and then we know the method in lecture number 43 we have discussed, where K1, K2 are function of Kp, Ki, Kd and the tau d, which is the time constant of the practical derivative controller. Then we have to select crossover frequency so that we can find out the controller integral gain. And this was referred in lecture number 43 in our this course, that how can we take this design for digital voltage mode control. So, in the digital voltage mode control, we have considered the small signal model of the analog voltage mode control along with this additional delay, and we have discussed in the small signal performance, as long as you operate close to 1/10 of the switching frequency, if you just incorporate this delay, they very accurate, I mean they match very nicely with the accurate discrete time model, but we have not come across the situation where when you go to the hardware demonstration, that it may lead to subharmonic instability which cannot be predicted by this model, but this model is good enough to characterize the small signal behavior. So, we have discussed this in lecture number 43 in this course. So, we know that if the K loop is the loop transfer function of the analog voltage mode control, then in the digital voltage mode control you can just simply multiply it by this delay transfer function, and this delay accommodate the controller computation, ADC conversion time as well as the DPWM delay. Then what we have discussed, this delay will not change the gain plot, but it will change the phase plot, as that means the gain plot will remain unaffected by this delay, but this delay will introduce an additional phase lag which is minus omega tau d, where omega is the instantaneous frequency and the tau d is the amount of delay that is introduced due to the digitization process. Now, we want to do analog to digital PID controller mapping by means of backward difference formula. So, we have already discussed that K1, K2, these are the polynomial, numerator polynomial of the controller, practical PID controller, and their coefficient can be written in terms of Kp, Ki, tau d and Kd. Then what we will do, in case of pole zero cancellation method in the voltage mode control design, which we have discussed in lecture number 43, that Q1 will be 1 by q omega 0, where q is the q factor and omega 0 is the undamped natural frequency, and the tau d, which is the derivative time constant, filter time constant, we can simply take this to be ESR of the capacitor, that means RC into C, the time constant due to the ESR of the capacitor. Then we already know that omega 0 for a practical buck converter will be R plus Re, and this Re is the equivalent resistance which consists of DCR, RDS on of the switch and DCR of the inductor, and this is the ESR, and R is the load resistance. Then Q format, this thing we have discussed. Then finally, we will get the Ki by suitably considering the crossover frequency that we have discussed. Now, if we can find out these K1, K2 values, then we can find out, that means we got K1, K2, tau d and Ki, and from here we can find out Kp, Ki, Kd and tau d. So, 4 equation, 4 unknowns. So, we can find out Ki, this is already obtained from setting the suitable crossover frequency. Then the Kp, which is the proportional gain for the continuous time case, it is Ki into K1 minus tau d. Then Kd is the derivative controller gain, and then once we get this, we want to convert into digital, because this is a backward difference formula, where the proportional gain will remain same whether it is a digital or analog, but the integral digital discrete time integral gain is nothing but the continuous time integral gain multiplied by the sampling time, and in this case it is a switching period. And the discrete time derivative gain will be simply continuous time discrete that gain like a derivative gain divided by the sampling time, which is a time switching period. By that way, we can get the digital PID controller gain and we can actually design the controller. So, let us go to the MATLAB case study, where we want to show that we want to design the PID controller, and this diagram shows the voltage mode control buck converter, and we already know the buck converter power stage, and in week 3 we have discussed in detail how to develop this model, MATLAB model. Step by step we have discussed sufficient detail. So, in this digital voltage controller, I think we have discussed in lecture number 22, 23, as well as we have also discussed other lectures also. So, in week 3 we have discussed how to implement that custom PID controller block using clock, it is a clock synchronized PID controller, that also we have discussed. So, this is proportional gain of the discrete time PID controller, this is the integral gain, discrete time integral gain, and the discrete time derivative gain. So, this thing we have discussed, and here the output voltage is sampled through by using a clock. So, it is flexible, that how to decide the clock sampling edge, that clock we can decide, it is a user choice. Then this sample goes and it is subtracted from the reference voltage, and then it goes to the controller, and the controller generates the control output voltage, and it is compared to the sawtooth waveform. And actual digital realization, this sawtooth can be generated by using either a counter or if there are other architecture that we have discussed in week 3. Once it is generated, then this is a trailing edge modulator, then the gate signal will be generated. Now, we want to go for design of the PID controller. So, we will follow the traditional continuous time PID controller design, and this we have discussed in our earlier NPTEL course, that means control and tuning method, where we have discussed in lecture number 34 and 35 in detail how to design this PID controller. 34 lecture is dedicated to we have discussed in detail about the PID controller design by means of stable pole 0 cancellation. Here we are setting the control voltage 10, it is again user choice. The sampling time, as we are sampling 0.1 times before, that means I will show you, first we are sampling, then we are switching. Now, for the PID controller design, we want to set a crossover frequency, and we are choosing the crossover frequency 1/20th of the switching frequency. Then all other controller parameters are decided, because we have discussed that we are using stable pole 0 cancellation. So, first we need to know what is our desired crossover frequency, and accordingly it will generate the integral gain, and then we can find out, and tau d, that is a practical PID controller, the derivative time constant, and that is used to cancel, that means that particular pole is used to cancel the ESR 0. So, we have discussed in detail. Once we get all these Ki and the continuous time controller, then we know this, we are actually using a stable pole 0 cancellation. That means the controller numerator is Ki times, we know that 1 plus K1s plus K2s square. So, that term used to cancel the denominator of the converter poles. That is why from there we can write K1 equal to 1 by Q, that we have discussed, Q into omega 0, K2 equal to 1 by omega 0 square, and Kp can be obtained from this K1, K2, Ki and tau d. So, these things are written. These are all analog controller gain. Then we have to use a backward difference formula, that means the proportional gain will remain same. Integral discrete time gain is the continuous time integral gain into t, and discrete time derivative gain is nothing but continuous time derivative gain divided by t. So, now we want to first run this simulation, and first we want to see that if we go to Bode plot, this is a continuous time transfer function, and I want to show that if we go for let us say we want to check what are the stability margins. So, you can see we are operating using 500 kHz switching frequency, and this is, you can see the frequency is 25 kilohertz, that means we are using 1/20th of the switching frequency, and phase margin is 90 degree because the phase is 90. So, phase margin is 90 degree. Now, this results into a transient response. We have applied a what kind of transient? Here we have applied a 10 ampere load current transient, and we have used 12 volt input and 1 volt output, and all the parameters we have taken the earlier parameters, which like L equal to 500 nanohenry, C equal to 200 microfarad, then T equal to 2 microsecond, 12 volt input, 1 volt output. So, once we get, you will see the transient response by means of stable pole zero cancellation is not good. So, if we want to get better response, one way you can increase the crossover frequency, instead of 1/20th, let us say 1/8 of this, and if we again run this simulation, we will see that it is somewhat better because we want to reduce the overshoot undershoot, but we have discussed beyond that 1/8 or even 1/10 will be the good choice. The model validation will comes into picture, that we have discussed in our earlier course. So, we do not want to design using small signal base beyond this bandwidth. So, this is the response that is coming from the output, which gives rise, the settling time is, here you can see we have applied a 3 millisecond, we have applied the transient, and if we want to zoom out, we will see it takes around 0.2 millisecond settling time with an overshoot of around more than 60 millivolt, and the undershoot is somewhat around 120 millivolt, which may not be acceptable. I mean, that is not a good sign by the means of this stable pole zero cancellation. Then we want to discuss the alternative method, and this method is discussed in lecture 43. In the alternative approach, the same thing, same PID controller, but right now we want to decide it is not any pole zero cancellation. So, we will take Kd, that is the derivative gain, to be 0.2 times C, and the tau d is T by 10, which earlier we have cancelled, tau d we have taken to cancel the ESR0. Here we are not doing anything, we are just taking the derivative gain 0.2 times the capacitor value, that is the output capacitor, tau d. But this design we have not discussed sufficient detail the methodology, but I want to bring out that the derivative action actually gives rise to some kind of voltage derivative, carries some information of inductor current along with the load current feed forward. So, you want to utilize that information. Then loop transfer function. So, we set Kd and tau d, tau d we have taken T by 10. So, you can continue to take T by 10 here. So, it should be T by 10, T by 10. Then Ki, you can take this value, which is nothing but, from here you can write Ki equal to alpha times Vm omega c divided by V in, where for choice of Ki we have taken as if omega c equal to your switching frequency by 20, that is why we have chosen, but again we can play with the integral gain, but this is a typical choice. So, we are not deciding omega c yet, but we are choosing the Ki by taking 1 omega, that is switching frequency by 20 times, that is a Ki gain. Then rest we have to decide Kp, and the Kp can be decided to achieve gain crossover frequency somewhat higher than 1/10 of the switching frequency. So, let us go to the alternative method in that, and we want to compare the result. So, we are going to alternative method and we want to plot on top of that to see what is the response. That means, we want to compare the response, and let us go to, we will take this dotted dash line to see the response. That means, we want to compare. So, in the alternative method, we have considered Ki to be 20 times, that we have discussed. Kd we can take 0.2, no issue, and Kp we have selected, and we will see what is my crossover frequency. Let us first run it. So, we are running it and we want to check the response. So, before we run, let us go to the MATLAB Bode plot. So, here we want to convert into unit hertz, then we want to check the stability margin. So, the second method, we are achieving little higher crossover frequency, but here it shows the phase margin is around 80 degree, whereas the stable pole 0 cancellation it was 90 degree, and crossover frequency is little less. But if you see the response, transient response in both the cases, I want to show that dash line is coming by alternative design method, and under steady state they must be identical, that we know. Okay. So, now if you go to the voltage recovery, so you can see the dash response is much better because its settling time is 0.2 millisecond, that means 20 microseconds. It just take 10 cycles, whereas the other method pole 0 cancellation is a non-robust method, it takes longer cycle, and also there is no overshoot as such for the second case. That means, we are talking about this particular response, there is no overshoot. So, which means we can get a better design by considering the derivative action as the load, it is carrying some load current information, inductor current plus load feed forward. So, viewing from that angle we can better design. So, what is the problem in the output impedance? Because in stable pole 0 cancellation we are trying to shape the loop, but if you recall the output impedance expression, it is the open loop output impedance divided by 1 plus loop transfer function. So, whatever loop you shape, in the numerator you still have the open loop output impedance, and that creates a problem. So, there are alternative way to shape the output impedance, and that we have discussed in lecture number 36 in our earlier NPTEL course, the control and tuning method. That means, it turns out to be a simple lead compensator will be good enough, but in the digital control method or the alternative design method, we can shape the PID controller, and accordingly we can get the discrete time PID controller gain. So, that means, we have learned that this alternative method can better handle the load transient performance, and we can convert this PID controller gain Kp, Ki, Kd by suitably scaling those from continuous time to discrete time. Now, we are going to the boost converter voltage mode control, because this class is mainly to show MATLAB simulation. So, in this converter it is analog voltage mode control, and then in this control analog voltage mode control we have this all controller in analog continuous time, and what are the methodology to design we have discussed in lecture number 43. We have discussed about the summary of steps. Number 1, we select the crossover frequency by setting some fraction of the RHP0. Okay. Then we will compute the phase margin, that how much phase margin you want. So, for 0.3 times, what is the phase margin that we are getting? Is it now that we know in case of continuous time voltage mode control boost converter design, we have discussed in lecture number 36 in our earlier NPTEL course, I think 36 or 37, where is the voltage mode control design. So, there by means of stable pole 0 cancellation, we can shape the, by setting the suitable omega c, we can find out whatever my phase margin. Similarly, we can also design by setting phase margin, and it will accordingly set the crossover frequency. But in case of digital control, we have an additional term that is coming due to the, that is additional phase lag due to the delay in the ADC conversion and controller computational time. So, we have to accommodate and then we need to check whether for the given time delay are you able to meet the required phase margin at least 45 degree or above. If not, then we have to again reduce the crossover frequency by scaling down this factor, and then we have to iterate the same method step and check whether the phase margin is met or not. Once it is there, then we will set the Ki, the integral gain, which is omega c, that is coming from this value into 1 minus d whole square by Fm into Vin. So, if that is set, then we got Ki. Once we get Ki, then since we have made stable pole 0 cancellation, so we will get all the other parameters. So, how do we get? That means this is the PID controller. We already got this expression of Ki from by setting our crossover frequency to meet certain desired phase margin. Then we can get the Kp from this parameter. These all 4 parameters are and 4 equations. We can find out individually the proportional gain, derivative gain in continuous time. Once we get, then we have to convert them in discrete time by means of backward difference formula, where proportional gain will remain same. The discrete time integral gain is the continuous time integral gain into sampling time, then a discrete time derivative gain is continuous time derivative gain by sampling time, and this we have discussed in lecture number 43. And we want to summarize that if you want to go for pole 0 cancellation method, stable pole 0 cancellation for the buck converter, we have already discussed the case study of buck, and for the boost, what will be the final expression of the Kp, Ki, Kd as well as the tau d values. So, that also we have discussed in lecture 43. Then we need to convert this continuous time controller gain into discrete time controller gain, and by that way we can set the controller parameter and we can implement whatever digital control platform we are using. But we have also discussed the alternative method. In the alternative method, we have already shown the simulation case study for buck converter, and we show that we have observed that load transient response is much better using this alternative method compared to this traditional method. Now we want to see a case study for the boost converter using the traditional pole 0 cancellation method that we have discussed, and then this method of this how to set this Ki, Kd, because here we will take the Ki to be worst case RH0, because this sets something like omega c worst case, it is the worst case omega c. Then alpha Vm by Vin, this is our voltage mode controller peak voltage, Vin is the input voltage 1 minus d whole square, and tau d T by 10, and then Kd 0.5 time output capacitor, and we have to take the Kp such that some phase margin, required phase margin is met. So, let us go to the MATLAB and we want to show. So, these are the earlier voltage mode control case study. So, we want to go to the MATLAB and we want to open. So, this was for the buck converter. Now, we will go for the boost converter. So, in the boost converter, we want to first open the boost converter PID controller case study, and I can show you that this is the diagram of the boost converter. This digital voltage controller is exactly structurally same as buck, only the parameter will be different, but the boost power stage we have already discussed how to implement in MATLAB custom simulation. So, we are not going to discuss again. Here we want to design the boost converter by means of stable pole 0 cancellation. So, that is why design based on the bandwidth, and we know that we can also design based on the phase margin. So, we will select P means what is the fraction of RH0 that we want to create the bandwidth, accordingly it will create phase margin, then you will get K1, K2 all these values, and finally it will show the digital PID controller value that we have discussed. Here we are considering a load step of 1 ampere load step for given initial load current of starting value R equal to 2 ohm, and let us run this simulation. So, maybe R equal to 1 ohm we can take. In alternative method R equal to 1 ohm, and we want to make a simulation case study of, let us say we want to make 3 ampere case study. So, here we will consider the RHP0 according to this expression. So, let us go back. RHP0 will be according to this expression, and we want to, because we want to make identical simulation case study. So, let us put it here. Okay. So, first I want to show R equal to 1. So, it is the pole 0 cancellation method. Okay. So, it is the pole 0 cancellation method. So, I have taken 0.3 times of this. That means, this is for the, okay, let us run again, because we will take 0.2 times. Now, we are going to show a stable pole 0 cancellation, the PID controller by means of stable pole 0 cancellation. So, we are taking initial load resistance of 1 ohm, and we want to apply a 3 ampere load step. So, let us say we want to design the crossover, that means the controller, PID controller, by setting the crossover frequency 0.3 times the RHP0. So, this is the response of the boost converter. Okay, so this is under voltage mode control, and now we want to go for the alternative method that we have discussed. So, in the alternative method, what we will do, we will design the PID controller by setting Ki to be same, which we discussed, and Kd, that means the fraction of omega c times 1 minus d whole square into RHP0 by Fm into Vin. Fm is nothing but 1 by Vm, Kd equal to 0.5 times C, and Kp for a small gain 1. So, let us run it and see what happens. Again we are setting 0.3 times, and you can see the blue color is the alternative design method, which is much better than the stable pole 0 cancellation. You can get a better response using stable pole 0 by by shaping the properly output impedance of the boost converter. But in this particular case, just by loop cancellation, that means if you take the red color, that was the response of the boost converter using stable pole 0 cancellation, where we are only shaping the output like a loop transfer function. But when you take the load transient, we have to consider the closed loop output impedance. So, in that point of view, it is somewhat difficult to handle. But if you go for the alternative method, since you are getting a fraction of derivative gain, fraction of that C, that means 0.5 C, and Ki we are setting same as the earlier formulation, but Kp we have taken a smaller value, and we get very much faster response as well as very well damped response for the boost converter using the alternative design method. So, in summary, I would say the second method, the alternative design method, may be more useful when you deal with the load transient response, and then you can accordingly convert all these Kp, Ki, Kd in the digital domain. So, in summary, we have discussed the design case study of digital voltage mode control buck converter. Then we have also discussed design case study of digital voltage mode control boost converter. We have shown MATLAB simulation case study for both buck as well as the boost converter digital voltage mode control. So, we want to finish it here for today's lecture. Thank you very much.